Well, let's start. We have proved the easy part of Vosper's theorem. So, what where we stopped? We stopped at the hard part of the theorem, where we know that AB is a critical pair. Right. We know that minimum between A and B is at least 2, and A plus B is A plus cardinality of A plus B minus 1, which is strictly smaller than P minus 1. This is our supposition. We have to prove that from this follows that A and B are arithmetic progressions, both. Right. How to do it? Lemma 1. It's here follows chain of lemmas. Lemma first is suppose AB is a critical pair such that A has cardinality K, B has cardinality L, both KL at least 2. Cardinality of A plus B is K plus L minus 1, and which is strictly smaller than P minus 1. And one more supposition, and also B is an arithmetic progression. Then A is arithmetic progression with the same difference. As B. So, what? Again, question? K plus L itself. Okay. Okay, let's prove it. Well, we know that B is arithmetic progression, so B is okay. Let's suppose A is arithmetic progression, then B is arithmetic progression, the same difference as A. Well, A is arithmetic progression, so A is A0 plus ID when I goes from 0 till K minus 1. Well, then A minus A0 multiplied by D inverse is what? What is this? Well, we extract A0, multiply by the inverse, so we have interval 0, k minus 1. All numbers in the interval, right? Okay. Well, let's denote it A prime. Well, B prime is B. Take any. Let's take any. Take any B0 from B, such that so and consider the set B prime, which is B minus B0 by D minus 1. Well, what we know about these sets? A prime plus B prime has the same cardinality as A plus B, right? Right? Moreover, A prime has the same cardinality as A, B prime has the same cardinality as B, and this is K plus L minus 1, right? So, pair A prime B prime also critical, right? Well, we have to show that B prime is also interval, right? Our aim is to show that from the supposition that A prime is interval, B prime also must be interval. Okay, how to do that? Well, let's consider, let's write down all the elements from B prime. B0, just order this B0. B0 is 0, right? Because 0 is contained inside. So B0 is a 0. B1, B2, BL minus 1, and also let's denote BL to be P. It's not an element of B. Is it prime? Well, it's actually element of B prime, but it's equal to B0. Right? Okay. Let's write it down. Look, what is A prime plus B prime? What is this? We add to B to is B0, B1, B2, BL. We just add to this one fixed interval. What do we get? What do we get? We just add to 0 the interval, to B1 the interval 0 to k, to B2 the interval from 0 to k minus 1, and what we get? We get part of this interval between 0 and B1, right? Either part or the whole interval, right? If these sums are intersect, we have two representations, or simply, right? Just because we add to B1 the interval, to B2 the interval, so on and so forth. This is, so, cardinality, this is union from I till 0, from 0 till L minus 1 of the interval. Bi till what? Till minimum between what? Bi plus 1, right? This is the case when we have the whole interval, right? Or Bi plus k minus 1. Right? No. Minus 1. Do you get? Bi minus 1, Bi plus 1 minus 1, because where the upper bound is this previous element, actually, because the Bi always will be inside A prime plus B prime, because A prime contains 0. So we already included this Bi, so we don't have to include it in previous interval. So this is Bi minus 1, Bi plus 1 minus 1, and Bi plus k plus 1 minus 1. Yeah, this. This is A prime plus B prime. Right. Next. This means as these intervals are not intersecting, this means that A prime plus B prime is some cardinality of this, is sum of lengths, cardinalities of these intervals. So this is sum for I from 0 till L minus 1. That's why, by the way, we introduced this BL, just because, well, for I equals to L minus 1, we have the part BL minus 1 from BL minus 1 to BL, which is P minus 1 till this one, right? Okay. Well, this is length of this interval. What is this? This is this part minus 1, right? Minimum between Bi and Bi plus 1 minus 1 and Bi plus k minus 1 minus 1. So let's sum this up, right? No, it's not, it's plus 1, not minus 1, plus 1. Because we start counting from 0, right? So these plus 1s are summing up to L, and we have this sum. I from 0 till L minus 1 minimum between Bi plus 1 minus 1, Bi plus k minus 1. Well, suppose for that means that this minimum that exists, suppose that for any I from 0 till L minus 1, Bi, what is shorter? Well, what is shorter? Well, it looks like, right. When we have this, when do we have, not minus 1. The difference between BIs, right? Minus 1. Right. Well, suppose this is shorter. The minimum attained for all i's in here. So BI plus 1, BI plus 1. So K is quite large. BI plus 1 minus BI minus 1, smaller or equal than BI plus K minus 1, suppose. Then, AA plus BI, AA prime plus BI prime is, what is this? This is L plus sum for I from 0 to L minus 1, BI plus 1 minus BI minus 1. And what we have that these minus 1s are also sum up to L, and these minus 1s, this L and minus L cancel each other, right? And we have this sum. This sum is, what is this? What is it equal to? It's B1 minus B0 plus B2 minus B1 plus B3 minus B2 so on and so forth, BL minus BL minus 1, but BL minus 1 is cancelled. So it's BL minus B0, so it's P. Right? Okay. But this is impossible because pair A prime B prime is critical. So this means A prime is plus B prime is not the P, but we got that this is the P. So A prime plus B prime equals to the P, and this is contradiction. Okay, next. So this means that exist I0 such from 1, 0 till L minus 1, such that the minimum attained on this position, right? So such that BI0 strictly plus k minus 1, strictly smaller than bi plus 1 minus bi minus 1, right? Okay. Which means then a prime plus b prime is at least L plus this minimum, which is bi 0 plus k minus 1. But this a prime plus b prime is k plus L minus 1, right? Well, which means that this bi 0 is what? Is no. This bi 0. Yeah, bi 0. That's all correct. Yeah, bi 0 is 0. Well, we can. It's positive, so it's at least L plus k minus 1. So, which means that this I0 is unique, right? Which means that for any I none which is not equal to I0, this bi plus 1 minus bi minus 1 is smaller or equal than bi plus k minus 1. Right? So, well, moreover, this moreover, bi plus 1 equals to bi plus 1, because this must be 0, right? It's not simply this bi 0 here. This is also sum for I non-equal I0, this minimums. And all this sum also must be 0. So for any I which is not I0, bi plus 1 must be bi plus 1. So what we have, what we showed that actually this bi 0 is 0. So it's B0 actually, and all others are sums of previous one. It's previous 1 plus 1. So this B prime is also integral. That's what we needed, right? Because from this follows that B is B0 plus ID. Look at the definition of B prime, right? It's B0 plus ID whenever I goes from 0 till L minus 1, everything is proved. I think, okay, it's good. Okay, so lemma 1 is proved. Lemma 2. This is short lemma, which saying that if AB is a critical pair, such that minimum between A and B coordinative A and coordinative B is 2, exactly 2, then A and B are arithmetic progressions with the same difference. Arithmetic progressions with the same difference. Not actually this one, pair such that this, and also we need this. A plus B is A plus B minus 1, which is strictly smaller than P minus 1. We actually need this condition, right? Okay. Well, how to prove that? Well, we just, one of the sets have 2 elements, right? Suppose, without loss of generation, because other case is the same, exactly the same in proof. That A is coordinative A is 2. Then A is arithmetic progression, right? Then A is arithmetic progression, is an arithmetic progression. Then by lemma 1, B is also arithmetic progression. By lemma 1, B is also arithmetic progression with the same difference. So we need these conditions in order to apply this lemma 1, right? We have the conditions inside lemma 1. Okay, so lemma 1 is proved. Okay, next. Lemma 2. Lemma 3. Suppose that AB is a critical pair such that minimum between A and B is at least 2. Also, cardinality of A plus B is A plus B minus 1, which is strictly smaller than P minus 1. Then pair D minus A is also critical. Here G is A plus B inverse, converse. Right. Well, proof. First, A plus B and D are non-intersecting, right? What this means? This means that D minus A, D plus A. No, D minus A. We have to show that D minus A cardinality is cardinality of D minus cardinality of, plus cardinality of A minus 1, right? We have to consider D minus A. So, which means that B intersect D minus A is empty set, right? So, D minus A has cardinality if cardinality of B is L, then D minus A in cardinality has at most how many elements? How many? It's inside complement of B, right? B. P minus B, P minus L. It has at most P minus L elements, right? We obtained the upper bound, lower bound. Cardinality of D is what? P minus K minus L plus 1, right? It's complement to A plus B. Which means that cardinality of D is P minus K minus L plus 1. Got it, right. Good. So this means that D minus A by Cauchy-Dewan port is at least minimum between P and G plus A minus 1, which is minimum between P and P minus K minus L plus 1 plus K minus 1. This P minus L is strictly smaller than P, so this minimum is P minus L. So we got lower bound, upper bound, which is the same, so D minus A in cardinality equals to cardinality of D minus plus cardinality of A minus 1, and this is strictly smaller than P minus 1, because L is at least 2. So we showed everything. Good. Lemma 4. Suppose AB is a critical pair such that minimum between cardinality of A and cardinality of B is at least 2. Cardinality of A plus B equals to cardinality of A plus cardinality of B minus 1 strictly smaller than P minus 1, and another supposition, and A plus B is an arithmetic progression. Then A and B are arithmetic progression with the same difference. Let's show this. Well, by lemma 3, the pair D minus 1, which is A plus B, and A plus B complement to A plus B and minus A is also a critical pair. A critical pair. Right? Moreover, this pair is satisfying. This pair also satisfying these conditions, right? Minimum between cardinality of G and A is at least 2, and this also, right? Satisfying star and star and double star. Right. Well, we know that A plus B is arithmetic progression, right? Since A plus B is an arithmetic progression, and then A plus B complement also arithmetic progression, right? How to show this? Is also arithmetic progression. How to prove it? That the complement in ZP to arithmetic progression is also arithmetic progression. Why? Well, suppose this is C0 plus ID whenever I goes from 0 to K plus M minus 2, right? Then this is this is what? The complement is what? This is C0 plus ID whenever I goes from K plus L minus 1 till P minus 1. So this is also arithmetic progression. Well, which means that by lemma, by lemma 1, by lemma 1, A is also arithmetic progression. Is an arithmetic progression with the same difference as A plus B has, right? With the same difference. With difference D. Right? But pair AB is critical one. So, and A is arithmetic progression, so means that B is also arithmetic progression, again by lemma 1, with difference D, right? B is an arithmetic progression with difference P, D. So, everything is proved. So, we have to prove, we have these conditions, and we have to show that A plus B is arithmetic progression. Our A, we just changed our main problem to the problem of proving that A plus B is arithmetic progression. Right, okay. Lemma 5. As far as I remember, there are 6 lemmas. No, there are 5 lemmas. Lemma 5. Well, this lemma states that suppose that AB is a critical pair such that first, cardinality of A is K, and this is at least 2. Cardinality of B is L, and this is at least 3. 0 is an element of B, is our suppositions. And also, naturally, K plus L minus 1 is strictly smaller than P minus 1. Then, there exists element E from A. such that pair AE BE is a critical first. Is critical. With properties. This property first, AE plus B is A plus B is first. Second, second this, B is in cardinality is at least 2 and strictly smaller than cardinality of B. That's all. Well, that's all we need. Right, let's prove this lemma. Well, first, let's show that, let's denote X as, which is set of all the elements A from A, E from A, such that B is strict. It's subset of B, which is not equal to B. Well, first we have to show that this X is non-empty. Well, no. First, what we have to do? We have to do first. We have to show actually that X contains at least 2 elements, not even 1, but 2. Right. Well, okay. First, for any E from A, what we have? We have to show that AE plus B is equal to A plus B. Well, A plus B is at least in cardinality by properties of E transform. A plus B is subset of A plus B, right? So A plus B is greater or equal than E plus B, right? But A plus B is A plus B K plus L minus 1. Right, but A plus B by Cauchy port is what? Is minimum between AE plus BE minus 1 and P, which is again minimum between cardinality of A plus cardinality of B is cardinality of A plus cardinality of B. This is main property of E transform. So this is which is K plus L minus 1 by property of this 1/3, right? All right. Well, so which means that cardinality of A plus B equals to cardinality of A plus B. And also this means that since A plus B is subset of A plus B, this means that A plus B equals to A plus B. Right? This is true for any critical pair, actually. Moreover, this E is inside A, but A is subset of A plus B because B is contained B contains 0, right? So everything is correct. So this B is non-empty. Okay. Next, we defined this X. Well, we shall show that cardinality of X is at least 2. Well, how to do that? Well, what we know about this? Well, if denote Y to be converse the opposite set, all the E's from A with property B equals to B. Complement set, right? So suppose Y is empty, then X equals to A, and cardinality of X is cardinality of A, which is at least 2 by conditions, right? So if Y is non-empty, then what we can claim, for any E from Y, we have that what? We have that that B intersect A minus E is B, right? Which means that B is B subset of A minus C. That's correct. For any E in Y. Which means that A plus Y is subset of A, B plus Y, right? Well, B plus Y is subset of A, which means that B plus Y contains at most K elements. Well, let's look at it. K is at most B plus Y, which is by Cauchy import again, minimum, at least minimum, between b, cardinality of b plus cardinality of y minus 1 and p. Well, what this means? This means that, well, cardinality of b is L, cardinality of y is k minus cardinality of x, right? Because y is complement of x to a, right? Right? Well, so this is cardinality of y is k minus cardinality of x minus 1. So by property this one, this minimum attained in here, right? So cardinality of x, k is at least L plus k minus 1 minus cardinality of x minus 1. Which means that cardinality of x is at least L minus 1. Right? Which is at least 3. Or 2. At least 2. That's all. That's all about the first part. So x contains at least 2 elements. All right. So what the second part is, well, we showed that there exists E, at least 2 E. There exists at least 2 elements E from A such that B is strictly smaller than B. We have to show this part. We proved this part. We proved this part. We have to show this part, right? So we have to show that we can subtract E from X such that B is contains more than one element. Okay. Suppose that for any E from X, well, BE is one element set. Well, look, this B, let's look at it. This B is A, this B intersect A minus C. E from A, element from A, right? So 0, this set can always contain 0 because 0 is inside B and 0 is inside A minus E, right? This intersection contains 0, right? Well, so if this is one element set, so this is exactly 0. So this is set containing only 0. Good. If we denote, if B prime is B without 0, then what? Then B prime, then for any E from X, B prime E is empty set. What this means? This means that which is B intersect A minus E. So which means that B prime intersect A minus E. Right? So which means that B prime intersect A minus X. B prime and A minus X is are non-intersecting, right? Well, what does from this follows that A minus X has at most how many elements? It's lying inside a complement of B prime. So this number of elements is at most P minus L plus 1, right? B prime contains L minus 1 element. So a complement of B prime contains P minus L plus 1 elements, right? Well, by Kashidwan word, this is at least, this is at most P minus L plus 1, and at least minimum between A, X minus 1 and P. A contains k elements. K elements, right? X contains number of elements which we don't know, and P. Right. Right. Natural, right. This is too good. Well, yeah, right. We have to transform this bit a bit. Look. Well, B prime plus C intersect A is empty set, right? For any E is in X. Well, which means that that B prime plus X is non-intersecting with A. but B prime plus X is subset of A plus B, right? So which means that b prime plus x is subset of a plus b without a, right? And we have much better upper bound for b prime plus x. Upper bound is k plus l minus 1 minus k, right? Which is l minus 1. Well, lower bound is bi-Cauchy Davenport for b plus x is this one, it's minimum between b prime plus x minus 1 and p. Well, b prime has l minus 1 elements. X has, well, I don't know, at most k element, right? K elements. Minus 1. So, no. Combination of x. Let's leave it like this. And upper bound is l minus 1. Well, but this means, so this means that this minimum is attained by this property, by this condition. On this part, so this is a x plus l minus 2. So we got x, cardinality of x, plus l minus 2 is at most l minus 1. So which means that x has at most one element. This is contradiction. Well, we showed this part, that we can find element of x such that B has at least two elements. We excluded the case when for any E from x, this B has one element. Okay, everything is good? Okay, well, we're ready to prove Wasper's theorem. Well, we proceed by induction on cardinality of B. Induction on cardinality of B. Base. Cardinality of B is 2. Well, by lemma 2, remember, by lemma 2, from this supposition follows that A and B are arithmetic progressions, right? By lemma 2. A and B are arithmetic progressions with the same difference. Well, well, the step, inductive step. Well, suppose we showed everything for, suppose, theorem is proved for all B such that cardinality of B is at most k minus 1, for example, k at least 3. Right. Let's consider any critical pair and B, A and B, satisfying first minimum cardinality of A is K, which is at least 2. Cardinality of B is L. Well, if cardinality of A is 1, everything is clear, right? Because one element set is our arithmetic progression, and by lemma 1, also everything is arithmetic progression, right? No. Yeah. Well, our limitations was minimum between A and B is 2. So cardinality of A is at least 2. Cardinality of B is at least 3, right? Now is at least 3 because it's an inductive step. Right, and A plus B has cardinality K plus L minus 1, which is at most P minus 1. Right. Well, by lemma, we didn't, we want to apply lemma 5, right? But in lemma 5, we had 0 inside B. Well, let's consider any B0 from B and take the set B prime, which is B minus B0. Then pair A B prime is also critical, so satisfying these conditions. Right? Then A B prime is also critical. Satisfying from 1 till 3. Right. Well, but B prime contains 0 also. By lemma 5, there exists E from A such that BE, the pair such that AE plus B is equal to A plus B, and and also BE contains at least two element and strictly smaller in cardinality than B. And also, well, pair AB is critical, right? AB is critical pair. Is a critical pair. What this means? This means that by induction hypothesis, right, we just reduced cardinality of B, right? And we still have this condition that B cardinality of B is at least 2, right? So we still in these restrictions, well, if we change this 3 to 2, right? We're still under condition that minimum A, E, B, E in cardinalities of A, E, and B at least 2, and A, E plus B minus 1, in cardinality of E plus cardinality of B minus 1, is at most strictly smaller than P minus 1, right? So we can use our induction hypothesis, right? By induction hypothesis, we have AE and BE are arithmetic progressions with the same difference. With the same difference. But AE plus B is A plus B. And AE plus B is arithmetic progression, right? So, but A plus B equals to AE plus B, and AE plus B is an arithmetic progression. Is an arithmetic progression. Because we sum up to arithmetic progressions with the same difference. Right. And this progression also has the same difference. Right. So A plus B is arithmetic progression. Then by lemma 3, and B also arithmetic progression with the same difference, right? Because we proved that A plus B is arithmetic progression, and a pair is critical, satisfying these restrictions. With the same difference. Well, that's all. The hardest part of Vosper's theorem is proved. Well, notice that we have the same difference inside all these progressions, right? This progression, these progressions have the same differences. That's all. Questions? well, applications to Wasper theorem. I'll give you one application of Wasper theorem. But well, let's finish today's lecture. Next lecture, I'll start with application of Wasper theorem. After application, I'll start next one. Well, let's think what it would be, because I don't want to give you Kneser's theorem, which contains lots of group theory. Yes. So the last part, what did you say? The last part, I don't want to give you Kneser's theorem, which contains lots of group theory. So I want to skip this theorem. I'll think what topic will be next one. Well, after Wasper's theorem. Okay, let's finish.